I'm Mrs. Rezak, and this is my resonance demonstration. So in order to talk about resonance, I'd like to first address the concept of a fundamental frequency. So the fundamental frequency is the lowest vibrational oscillation of a disturbed medium. So every object or every medium has a fundamental frequency that it will vibrate at when disturbed. So as an example, I have these plastic tubes, which are called boom whackers, and I have different lengths, and when I disturb the air inside the tube, it vibrates and makes a sound. So this red boom whacker is approximately a C. The orange is a D. Green is F. And B is, the purple one is B. So each one of these boom whackers has a different fundamental frequency. And all that means is that when I whack them, the air inside vibrates in such a way that it produces that sound. The reason each one produces a different sound in this case is because they have different lengths. So that is fundamental frequency. The air inside resonates at a certain frequency. Two things with the same fundamental frequency, or that tend to vibrate at the same fundamental frequency, will vibrate in sympathy with one another. So this is one of the ways that resonance is manifested in nature. This device is specifically designed to demonstrate a sympathetic vibration. So what I'm going to do is disturb this tallest medium, and so the tallest wire, if I disturb it, we can observe on the other side that the tallest medium on the other side begins to vibrate in frequency, in sympathy. The reason that happens is that there's tiny little forces that travel through the air and at just the right moment cause the other object to vibrate. So a good example of resonance would be swinging on a swing. So when you swing on a swing, you need to pump your legs at just the right moment so that you swing higher. So when you pump your legs at just the right moment, you see an increase in amplitude. This is the exact same thing, only it's not a swing. What's happening is that the tall medium here is providing a force at just the right moment on the other tall medium on the other side and causing it to vibrate. If I disturb the shortest wire, only the shortest wire on the other side begins to vibrate in sympathy. If I disturb the medium size wire on the other side begins to vibrate. So this is known as a sympathetic vibration, and it is a form of resonance. If you play a string instrument, you are familiar with a sympathetic vibration. For example, if you were in orchestra and you have your violin or cello and another instrument, someone else plays an open A, for example, you might notice that your A string begins to vibrate in sympathy because both the A strings have the same fundamental frequency that they vibrate when disturbed. Here's another example. I have two tuning forks. These tuning forks are both tuned to C, or 256 hertz. So when I strike one, I'm going to cause it to vibrate. The tines on the tuning fork are going to move in and out. So they're going to disturb the air, and that air is going to put another force on the other tuning fork. So I strike this one. This one's no longer vibrating. The sound is coming from the other tuning fork. These boxes on the bottom are just to amplify the sound, very similar to the body of an acoustic guitar. So I just want to show you that again. So this. So the other tuning fork vibrates in sympathy. If I take a rubber band and I put it on one of my tuning forks, I'm essentially changing the fundamental frequency of the other tuning fork. So now this one has a different frequency. So when I strike the first one, the other one no longer vibrates in frequency because now it has a different fundamental frequency. However, if I strike both of them at the same time, something really cool happens. So check it out. So I think you could hear that wah, wah, wah sound. That's a phenomenon known as beats. And again, if you play a stringed instrument, you're probably familiar with this phenomenon because you know whether or not you're in tune. If, say, you and the person next to you play the same note and you hear that wah, 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 those beats, you know one of you is out of tune because you're not playing the same frequency. So frequency in sound is related to pitch. So the higher the frequency, the higher the pitch of the sound. In beats, what we see is this constructive and destructive interference. So the two sounds are fully superimposed, or they're in the same place at the same time, and when they reach your ears. And so sometimes they will interfere constructively and we hear the louder sound, and then at other times they interfere destructively and we hear the quieter sound. So amplitude is related to volume or loudness, and so constructive interference means a louder sound. Destructive interference means a quieter sound. So for beat frequency, or the frequency of the beat, the wah, 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 the beat frequency is equal to the difference between the two frequencies. So if this tuning fork has a frequency of 256 hertz, the one with the rubber band has a frequency of 238 hertz. When those two sounds reach your ear and interfere, you would hear a beat frequency of 2 hertz, the difference between 258 and 256. So resonance is defined as the reinforcement of a vibration by reflection from a surface, that's known as a standing wave, or by the synchronous vibration of a nearby object, which we just discussed is a sympathetic vibration. So to demonstrate resonance in a standing wave, I have a device set up here, and normally we would do this in class. Page 94, you have a resonance lab, and this PVC pipe is filled with water, and inside I have another PVC pipe that has a graduation on it, so I can measure the length of the column. So when I take the inner PVC pipe out, what I'm doing is changing the length of that air column. So what I'm going to do with this setup is I'm going to use my tuning fork app, and I have this set to 440 hertz. So the frequency of the sound is going to remain the same, and I'm going to project the sound into the tube, and I'm going to change the length of my air column. So the water provides a fixed end for the sound to reflect from. The top, the opening, would be a free end. Hopefully you can hear right there, there's an increase in the amplitude, or an increase in volume. And that's happening at 18 centimeters. If I continue to lengthen my air column, right there, at 59 centimeters, I hear another increase in amplitude. So 59 and 18. So I'm going to illustrate that here on the board. The first length was 19 centimeters, and the second length was 59 centimeters. Because the water provides a fixed end, I know that has to be a node. Where I'm hearing the increase in amplitude has to be an antinode, or an area of constructive interference. So the very first antinode would have a waveform that looks something like this. So that is 1/4 of a wavelength. So the length is equal to 1/4 of a wavelength. So wavelength would have to equal 4 times the length of that air column. The second antinode we heard at 59 centimeters. So I'm going to have my first antinode and second antinode. So it would look something like this. So here is my first antinode, that's the 19 centimeters, and then up here at the top is my second antinode. So this length is equal to 3/4 of a wavelength, so length 2 equals 3/4 of a wavelength, so wavelength equals 4 times the length over 3, or 4/3 the length. So what I can do is just subtract out this 19 centimeters right here to get from antinode to antinode, and that is what's intended to go in the third column on page 94. So from antinode to antinode is half a wavelength. So this length equals half a wavelength. So wavelength equals 2 times the difference between L2 and L1. So L equals L2 minus L1, which would be 59 centimeters minus 19 centimeters, which is 40 centimeters, or 0.4 meters. So 2 times the length of 0.4 meters would give us the wavelength of that sound of 0.8 meters. So I know the wavelength, I know the frequency, so I can calculate the speed of sound in air. So we know velocity equals wavelength times frequency. I measured, using my air column, a wavelength of 0.8 meters. I have a frequency of 440 hertz. The speed of sound in air would simply equal 0.8 times 440, which is 352 meters per second, which is pretty close to our accepted value of 343 meters per second for the speed of sound in air at standard temperature and pressure.
An example of beats tells us the sound from a 500 hertz tuning fork and a vibrating string of unknown frequency produce beats heard at a frequency of 2 hertz. So what we're given is frequency 1, which is 500 hertz, and the frequency of the beat, or the beat frequency, is 2 hertz. What we want to know is the frequency of the second sound. So the beat frequency, or the frequency of the beats, are equal to the difference between the two frequencies, so F1 minus F2. So the so the frequency of the second sound would have to equal the frequency of the first sound plus or minus the beat frequency. So the second sound could be either 498 hertz or 502 hertz. Part B asks, what effect would placing a small piece of tape to the end of the above tuning fork have on the beat frequency? So placing the tape on the tuning fork would decrease the frequency of the tuning fork because it would have more mass, so it wouldn't be able to vibrate as quickly, so it would undergo fewer cycles per second. So we can definitely say the tape would decrease the frequency of the tuning fork. Now, as far as the beat frequency, it would depend. So it would depend on whether we had a string of 498 hertz or a string vibrating at 502 hertz as to whether the beat frequency would increase or decrease. For Doppler effect, I posted several videos for you and on with this video. And so you want to look at the one titled Doppler effect, and the Big Bang Theory one is mostly for fun, but it will help you remember the Doppler effect. So take notes, and I'll see you on Wednesday.